the Dodin torus to HR, factorized through H prime R. Is the no? Is the X? You have a group H prime Q over Q, and you extend it to R. Oh, no. H prime Q is the Mumford group. Yes. Okay. Yeah. H prime Q is the Mumford group, and yeah. Okay. Okay. So definition. Okay, maybe one. So I have to define special points in this language. So there will be the special subvarieties of dimension 0. And when you look what it means, it's defined by a sub-Shimura datum. So say HXH, where with HQ, a Q torus. And okay, if you come back to the definition of moduli space of principally polarized abelian varieties, you will find the points with sufficiently many complex multiplication. So I will give somehow an opposite definition. So a strongly special subvariety. So it's defined by definition. It's defined by HQ XH with HQ semi-simple, so which means that you have the connected center of HQ is trivial, okay? And the last thing that I have to define is the following notion. Fix a Q torus T, TQ if you want, inside GQ. A T spatial subvariety is associated to some Shimura datum HQXH with when you write the decomposition of HQ as a semi-direct product of the connected center by the derived group, the center is T. The connected center is T. Okay. So in this situation, T equals 1 is admitted. And if you want, this means that one special is by definition strongly special. Okay. So, okay, now I can state some results. Okay. Okay. Okay, so the derived group is generated by the commutators, and it's yeah. Okay, so okay, so you always have for reductive group a semi-direct decomposition of the derived group by the connected center, and this means that the intersection of T and this group is finite. It's part of the theory of reductive. Okay, so the first theorem, so it's about equidistribution and essentially with Clausel, is the following. So let Zn be a sequence of strongly special or T-special subvarieties. Then, okay, I have to change the choke. Then, there exists a strongly special subvariety Z or T special such that you have the two following property. There exists a subsequence such that there exists a subsequence Z and K with mu Z and K converge weakly to the canonical measure on Z, and B Z and K is inside Z for K big enough. And maybe here, as my variety are not projective, I should say that this means that for all F continuous and bounded, the integral over S of F times mu Z and K tends to the integral of F against mu Z. Okay. So I try to come back to explain more about the proof of this theorem later, but I try to explain more of the strategy of the proof of the Andreae conjecture. So, okay, so the second step, so this is equidistribution. Then I have a first theorem in Galois theory. So Galois orbits. So I start by fixing F a number field over which S is defined. And it's a deep theorem that such a field exists. And here is the following statement with F, giving lower bounds for Galois orbit of special subvarieties. Okay, so I give some quantification. There exists a B strictly positive, and such that for all n positive, and for all HXH, a subchimera datum of Jx. Okay, right with So I just write the decomposition of HQ as a semi-direct product. But I assume that the dimension of T is strictly positive. Now, let Z be an associated sub-Shimura variety or species. So inside S, then the statement is the following. I take the set of Galois conjugate of my component, and I want to understand the number of components of such a thing. And I have a lower bound for this. And so I write this with the shape of a lower bound. So it's P power something depending on T. So I will explain every term just after. So these are related to compact subgroup of T and times the log of the discriminant of LT and power n. So I have to explain several things in this formula and to comment a little bit on it. So in this formula, so my compact open subgroup K can be chosen of the form product of the KP. And so I will define KT to be T of the AF intersected with K. And KTM is the maximal compact open subgroup of T of AF. So this is a product for all P of KTPM, and this is a product for all T of KTP. And okay. So the constant I of T is the cardinality of prime number such that KTPM is not KTP. So it's a finite set. And I take the number here. And the last thing is L, or LT, is the splitting field of T. Okay, so what means this formula? It means that you have two ways of having a big orbit. One way is when the discriminant of the splitting field of T is big, and the other way is when you have a lot of prime, this one is fixed, says, and you have a lot of P such that this is KTPM is not KTP. Okay, so now analyzing this formula, we proved the following result with FIF. So maybe so theorem 3. Okay, let Zn be a sequence of special subvariety of S. Such that the cardinality of the set of Gala conjugate is uniformly bounded. Then there exists a torus T and a subsequence Z and K such that Z and K is a T special subvariety. So somehow I have only finitely many choice for the center of the Mumford-Tate group if the Galois orbit is bounded. Okay. So where? P, I think it's, you have a lot of prime numbers, so it's the product of all prime numbers. Where? It's the set of prime numbers such that the P part of the maximal of the compact group is not the maximal compact. Okay. So the corollary is the alternative Galois ergodic. So how it works? You want to prove André-Hort, so you try to start with, you fix a subvariety Y of your Shimura variety, and you give yourself a sequence of special subvarieties. Then after possibly passing to a subsequence, at least one of the following two possibilities occurs. Okay, so maybe I continue here. But, this one okay, so the first possibility is in the case the Galois orbits are uniformly bounded, And in this case, we will know by combinations of this theorem. So I should say here, let Zn be a Zariski dense. So sorry. So Zariski dense in Y. Oh, sorry, it's here. I'm confused. So here, this is a Zariski dense. In Y. So in the first case, we know that if the Galois orbits are bounded, we will know that mu z n converge weakly to mu z for some z. Zn will be included in Z, which is included in Y for all, say for all n big enough. So I stop passing to a subsequence. And but this this sequence is Zariski dense in Y. So this implies that Y equals Z is special. And in this case, you're down. And the other possibility is, or the cardinality of the set of the Galois conjugate tends to plus infinity, and then start the work of Klingler and Yafaev. And in this case, they are able to prove that for n big enough, there exists Z prime n a special subvariety with Zn inside Z prime n inside Y. And the important fact is that here it's different. And as in the case of the Manin-Mumford conjecture, you can formally finish the proof from this. But this is the hard part. I mean, it's non-obvious at all. But okay, so I have no real time to explain too much this. I would like to explain more in detail the ergodic theorem. Yes? Yeah, so, okay. I said GRH at the beginning, but I should say, okay, all the ergodic theory is without GRH. The lower bound for Galois orbit use GRH in an unessential way. So we use it because we don't know how to do in another way, but it should be possible to remove it at this part. But in this part, GRH is used in a fundamental way. So here, there is really GRH and in a deep way, and there is no hope at the moment of avoiding GRH. Okay, so now I try to explain.
Why do you think in the first case you can remove GRH?
Yeah, I mean, it's really used in a very unessential way. I mean, proving lower bound for Galois orbits, say of CM points, for example. I mean, I think that people working in analytic number theory should take all the problems seriously. And I mean, we are not specialists somehow of this kind of question. And so as GRH was used, it was easier. But in principle, it's an important and nice question. But yeah, okay. So I mean, the intuition is that for modular curve, the lower bound for the Galois orbit of Cm points of discriminant D, it's d power 1/2 minus epsilon. So it's known, and it's really better than this, and it's a theorem. It's not and there is no GRH in it. So, okay, this is my feeling. So I would like to explain briefly the proof of the ergodic part, and it relies on Hartnell's theory, and I want to explain this theory. So here is the situation. Fix GQ a semi-simple group over Q. Define omega equals G of L plus divided by gamma for an arithmetic lattice gamma inside the Q point of G. And so we define the following set of connected closed Lie subgroups H inside G of R plus with two properties. Okay, such that the first thing is that the intersection of H with gamma is a lattice in H. And this implies that if you take the H orbit of a neutral element here, you find a very nice variety, homogeneous like this. And in particular, H in this situation is endowed with a canonical H of R. H invariant probability measure. I will call it mu H. Okay. Okay, so until now, okay, I have still a second definition to give for defining this class H. So okay, so the second thing, the second property is the following. Let L of H be the subgroup of H generated by unipotent one parameter subgroups of H. Okay, then L of H acts ergodically on H divided by H intersect with gamma with respect to mu h. And this means nothing but else that any L invariant mu h measurable set inside H has measure 0 or 1. Okay, so this is the definition of an algorithm. Okay, so until now I said nothing about my class, so why it's interesting. So, okay. So here are a list of properties. So let H be an element in H. Then there exists a Q algebraic group HQ inside GQ such that H is just the set of real point, maybe the connected component in the ordinary topology of a set of real point of HQ. And HQ is the Mumford-Tate group of H. So I mean the smallest Q subgroup of GQ such that HQ is inside H is inside HQ of R plus. Okay. So the class H is related to algebraic groups, and there is a very concrete description of this possible algebraic group. If H is related to HQ is an element of H, it really means that if you decompose HQ as the semi-direct product of is radical by the semi-simple component, Q-simple component as an almost direct product, then R, the radical, is in fact unipotent. And for all I in one R, if you take the real point of HI, which is a Q subgroup, this is not compact. Okay. Okay, so until now it's just a definition. Okay, so I can almost state the theorem of Hartnell. No. Okay, so I give one more property before. Okay, so let L be a subgroup generated by unipotent one-parameter subgroups. Then there exists a unique H in H such that so L is inside L of H inside H, and L acts ergodically on H divided by H intersected with gamma. Okay, so with respect to the natural measure, and the fundamental theorem, or part of the fundamental theorem of Hartnell, is the following thing. So, okay, in this situation, the group H is the Mumford group of L, essentially. And so let L be, as previously, okay, let L be a subgroup generated by unipotence, and H, so the Mumford group of L. So if you take the orbit of L passing through the origin, in general this orbit is quite awful, and, but you can take the completion for the ordinary topology, and the meaning, the relation between what I said before and the class H is that even though this orbit is quite awful, the closure is a quite nice homogeneous variety. Okay, so the closure of unipotent orbits is homogeneous. Okay, so I will need a more precise statement. So let P of omega be the set of probability measures on omega and Q of omega be the set of mu H with H. So I have this set of subgroups and associated, okay? Then you have the following theorem by Moses and Shah. Saying that Q of omega is compact. And so what it means, so it means that if mu n is in Q of omega, a sequence, then up to a subsequence, there is this H in H, and a subsequence mu and k converging weakly to mu H, and in this situation, Hn is inside H for H and k for k big enough if mu n is mu Hn. Okay, so this is a quite interesting result, but it's the hardest part is really a Hartnell theorem. Okay, and okay, so I have less than 5 minutes to explain the principle of the proof, but I try to say one word. It's compact for the weak topology, weak star topology. On P of omega, you have the weak star topology, and Q omega is a compact subset. Okay. Okay, so principle of proof. Okay, so now it seems that it will be sketchy. So you have your Shimura variety is something like the Hermitian symmetric space G of R plus divided by a maximal compact divided by gamma. And I define omega to be just G of R plus divided by gamma. And I have the associated class H defined in the previous section. So let Zn be a sequence of, say, strongly special for subvarieties. So associated to this, you have some subgroup, say over Q, and some Hermitian symmetric spaces, Xn. And so they are strongly special. So these are semi-simple. And using the definition by Deligne of what is Deligne's definition, this will imply that H and Q of R plus is in fact in my class H. And passing to a subsequence, I can assume that mu H n, and using the Moses-Shah theorem, for some H in H, and with the property that Hn is in H for n big enough. Okay, so the problem somehow, here is one problem. So you have this class H, and you have a set of mu H with HXH a probability, and okay, mu F, F, XF. Here, you have many more. You have a lot of such subgroups, and here you have fewer, maybe. And what you have to show, you have to prove that H, the limit that you find here, is related to Shimura varieties. Okay, so you have two problems. H could have a unipotent radical, and the more serious problem is that the component of H could, the derived group, if you want, could have a symmetric space which is not Hermitian. But in fact, okay, you prove that in fact one can reconstruct H, XH by knowing somehow that HQ there is inside HQ. HQ there N is inside HQ. And okay, using this information, you prove that HQ is associated to a Shimura variety. Okay, and really in one word, you have to face a second serious problem. Pass from G of R plus divide by gamma to S. And the main problem is that you have for each point in X, you have a way, you have a map, you have such a map, and if you start with a sequence of probability measure mu Zn, what you have to understand, how you construct mu Zn, you have to find a point xn, which is in xhn. And the problem is that you have to choose this one in this group, this Hermitian symmetric space. But when n moves, xn, you cannot have a fixed choice for xn. So, okay. So, so I have no time to explain, but we use for this part, I mean, if the quotient is compact here, there is nothing to prove somehow, because you can fix xn in some fundamental domains for the action of gamma. And for the general case, we use some theorem by Dany and Margulis on action of unipotent flows. So it's, okay, so I have no time to explain, and I'm already late, sorry.